The General Purpose Transformer, or GPT, has really transformed the AI landscape over the last few years. In this workshop, we'll learn about its origins and internal structure, and we'll build one from scratch. Hi, my name is Yufeng, and I'm a developer advocate at Google. Today, we'll check out the process of building a transformer on JAX using the Flax NNX library to build the model architecture, Optax for loss function and optimizer creation, and train on accelerated hardware with the help of Orbax and XLA. You'll get a taste of what development on JAX looks like, and be prepared to take your next step into the world of building and training AI models. Now, before we dive into the code, I want to set the stage a little bit and give some background on transformers. If you're already familiar with this and you want to skip ahead to the coding, please, by all means, feel free. I certainly won't be offended. When transformers and large language models were first coming onto the scene, they were made specifically for processing text. Nowadays, many large language models are what we call multimodal, meaning they can work with other modes of communication, including pictures, video, and audio. But how does a computer really know what any words mean? It all comes down to embeddings, a way to turn human understandable concepts into numbers that the computer can process and interpret. Initially, the entire vocabulary that a language model is expected to see is placed sort of in random positions throughout what we might consider a higher dimensional space. This is called the embedding space. Now, how many dimensions are we talking about? It might be hundreds or even thousands of dimensions. This allows the embedding to capture a lot of understanding and nuance about each and every term in its vocabulary. Then, through the training process involving looking at all of the text in its training dataset, these text embeddings are updated to reflect the meaning of the words and their relationships to one another. For instance, the word jump might be close to other physical activities and exercises, and it might also, perhaps along a different dimension, be close to terms about car repair and jumping a car. The key takeaway here is that when machine learning models handle text these days, they're typically looking at it through the lens of an embedding space, rather than simply the characters of a word that you and I see. If you want to learn more about embeddings, there are some great detailed explanations at the Machine Learning Crash Course at developers.google.com. And if you want to access some existing embeddings that already have a large vocabulary trained and ready for you to use, you can use text embeddings from Google Cloud. It even has multilingual embedding models. Now let's turn our attention to the real reason you're here, transformers. Depending on who you ask, it all started back in 2017 with the research paper famously titled "Attention is All You Need" from Google Brain. The concepts presented in this paper lie at the very heart of large language models today, and it led to further research of variations on the original ideas, many of which are still being developed and explored to this day. You can read the paper if you'd like. It's quite well written. In this video, we'll go over some highlights so we can better understand what we'll be doing in the code. The transformer architecture focuses on a novel operation called attention, hence the title of the paper, coupling it with a number of other operations that were commonplace among machine learning models at the time. Let's dig into this further. The task that the researchers were able to figure out with attention was a way to numerically calculate and describe the relationship between words in the context that they were being used. Moreover, it allowed the words themselves to be that guide as to the relationships amongst each other. The inputs to attention were three vectors called query, key, and value, typically referred to as Q, K, and V. You can think of the query vector as describing, for each word in a sentence or phrase, what other words it cares about. What is it looking for? The key vector is a way to represent what a word wants to present about itself in response to those other queries. And the value vector encodes what it kind of offers in the event of a good match. Another way to describe it is perhaps with a handshake, along with a gift exchange. The query is someone reaching out their hand, and the key is the other hand coming out to meet it. And if they successfully match up, then the value is what is then handed over if a handshake is established. There are a couple other things we see here in the attention formula, aside from Q, K, and V. First, there is the softmax function. What is softmax? Softmax normalizes the values coming out of Q.K, ensuring that they all sum to 1, and shows us which values are the highest. So if one value is minorly larger than the others, it might end up with a value of 0.8, while the rest sum up to 0.2. So it all comes together as 1. If the two biggest values are both about the same, right? It's like a tie for first. They might each have, say, a value of 0.4, while the rest of the values sum up to 0.2. Second, we see that Q.K is divided by the square root of D. D here refers to the embedding dimension used in our text embedding. So if we had an embedding dimension of, say, 64, we'll divide the entire dot product by 8. Why are we doing this? The reason is to scale down the value that gets passed into softmax. Even though softmax is going to normalize our values regardless, the way that it computes this means that the higher the absolute value of all the terms are, the more those resulting decimals get pulled to extremes. So instead of having values that are small and have kind of small differences, it might select the largest one, even if it's only larger by a little bit, and just make it way bigger. In other words, it makes the distribution sharper or peakier. All of this comes together to make what is called scaled dot product attention. The bottom diagram uses this and scales it up. So when we talk about multi-headed attention, it's referring to multiple parallel implementations of attention, all happening independently from one another. This allows the model to attend to different aspects of the relationships in the data. There's clearly a lot happening here in this diagram, and I cannot hope to explain it all in this video alone, otherwise we'll never get to the workshop part. A couple of particularly good resources are out there, which discuss the transformer in great detail. One is called the Illustrated Transformer, which goes through each operation in the transformer with fantastic animated graphics. Once you've gone through that and finished this video, you'll be really well set up to understand Chapter 4 of the free book titled How to Scale Your Model from DeepMind. That chapter is titled All the Transformer Math You Need to Know, and will help you better understand how all this code, numbers, and data work together with the incredible infrastructure used to train these models. We'll definitely be sure to put these links in the resources below. But wait, there is more. The whole transformer model, well, that's a lot more than just attention alone. For modern large language models, we'll mostly focus solely on the right half of this diagram and use it as a guide as we build our model. And so we'll come back to this diagram throughout this video to reference what pieces we need to implement next. Each of these lines shows how data is flowing. You'll notice that some of the arrows branch off and bypass certain blocks. This allows data from prior to a block to be combined with data after it's been transformed in some way. These so-called skip connections help the model stay on track as it trains, and is especially important in the early stages of the training process for these large models. You'll also notice that the far right side says NX. This is referring to the gray block being repeated n times. And when you zoom out to this level, the transformer model is actually quite repetitive. So if you were to draw out all those repeated blocks in the middle n times, they'd make up most of the model, with just a little bit at the start and a little bit at the end that is different. Okay, so that's all we'll say for now about theory. Let's get working on the actual code. There's a link in the description below to the notebook that I'll be working from. So if you want to go ahead and follow along, click on that link and open it up. The notebook can be run in Kaggle or in Colab. The only difference will be in what accelerators you can use and how the dataset will be downloaded. Otherwise, it will be identical, so choose whichever platform you prefer. Once you open up the notebook, click Copy and Edit so you can have your own copy to follow along. If you want to run the cells, make some tweaks, try things out for yourself. The first few cells focus on setup, imports, and data loading. So go ahead and run those to get things started. I want to note that in Kaggle, the data sets associated with the notebook are being loaded in the background while the notebook is starting up. So you might need to pause this video to let that finish, as downloading the dataset called Open Web Text here will take some time, as it's over 16 gigabytes and contains nearly 70 million text files. Open Web Text is a dataset that aims to replicate the dataset that was used to train GPT-2. The original dataset was not released, so Open Web Text is the best approximation that we have. On the Colab side of things, you'll need to do a bit more manual work to get this dataset situated. Scroll down to the section titled Prepare Data, so you can see how the notebook is being loaded from Google Drive. My recommendation is to download the Open Web Text zip file from the website where it's hosted. That's 12 gigabytes, and then you can unzip it into its 18 gigabyte form. So that's, add them together, carry the one, at least 30 gigabytes total of empty space that you'll need on your local disk. Then you can upload the two files, train.bin and val.bin, up to Google Drive, where Colab can then read it. This way, you won't need to download it every single time you run the notebook. The notebook defaults to reading from the LLM-pretraining/OpenWebText directory, but you're welcome to change that to point to wherever you end up saving those files. One final setup step that we'll do so that we can more easily monitor our training run is connect the notebook with weights and biases. Go ahead and create a free account there and retrieve your API key, which you can do directly at wmb.ai/authorize. Add that key to the secrets section of your notebook. Now, we're ready to train our model. Okay, back to JAX. When we run jax.devices, we can see what devices JAX can see, in particular when it comes to what accelerators are available. Now, if you're on Kaggle, you'll have 8 TPU v3 chips, while on Colab, you'll have 8 TPU v2 chips. Next, we're going to set up the device mesh, which will allow us to distribute our dataset and our model across these devices that we have available to us. In this case, we'll split up our data 8 ways across 8 chips, keeping a full copy of the model on every single chip. This is sometimes referred to as data parallelism, since the data is being split up and processed in parallel while the model remains whole and undivided. There are other ways to split up or shard our data and model. For example, you might split the data up 4 ways instead of 8, and then split the model in half so that each copy is distributed across 2 chips. Think of it as a 4x2 grid or mesh that contains 4 pairs of model halves and then 2 copies of each batch of data split 4 ways. Since we're aiming to simulate the results of GPT-2, our code uses the embeddings released with the GPT-2 model. We'll retrieve them using the tick token library. The next cell sets us up with a number of hyperparameters, which define how our training run will be set up. These numbers are focused around how best to utilize the hardware that we're training on. we'll be using the GPT-2 branch of the code with a batch size of 24 on Colab and 72 on Kaggle. This illustrates the difference, in part, between TPU v2 and v3. We can achieve a batch size that's 3 times larger with TPU v3. Now, let's check out the model structure of the transformer. We'll see how to use the NNX library, which stands for Neural Networks for JAX. And let's start from the top-level model construction function, the class called GPT-2, and then dive into various function implementations from there. So go ahead and scroll down to the bottom of that big cell that defines our model architecture. This class is how we bring together all the pieces of our model definition at the end and shows us the highest level abstractions of our architecture. At this view, we really just have the layers that are surrounding the transformer blocks, specifically the layers that come at the beginning and the end, as everything else is being taken care of inside the transformer block. At the top of the model is the embedding layer, which we'll define in detail above, followed by a dropout layer going straight into those transformer blocks. The number of blocks we have is actually configurable from those hyperparameters at the top of the notebook. So this easily allows us to scale the model up and down in size based on how big our infrastructure is and how big we want the model to be. For example, the GPT medium model has twice as many transformer blocks as this one, going from 12 to 24. On the other end of the transformer blocks is a layer norm, which helps normalize the output weights, followed by a final linear layer before the output of the model. Scrolling up to the next class, what do we have here is the token and position embedding class. This one is fairly short, and all it really does is put together the embeddings of the text, along with the position of the words. As we briefly touched on in the first section of this video, part of what makes attention special is that it not only understands what words mean, but also where words are. Notice that each of these classes inherits from the nnx.module and has an init method and a call method. The call method is where we really wire together those class attributes that are defined in the init function. So in this call function, we set up the position data, which is really literally a list of increasing numbers like 0, 1, 2, 3, and pass them into the position embedding that we set up in the initialization. And then we pass the input text through the token embedding that we created during the init, and then we literally just add them together. The next class we see as we scroll on up is our transformer block. This block contains the details of everything in the gray box from part 1 of the video, with multi-headed attention at its core, wrapped in a couple of layered norms and linear layers. Similar to the token and position embedding class, here there's an initialization and a call method. The init method lists out the various layers we'll be using, but the call method is where attention is really put together. We see that first it creates a multi-headed attention block, passing in the first layer norm as part of the input. Then it adds a dropout, but also adds in the original inputs here, whose values have not been passed through attention at all. This is how those skip connections we talked about are created in code. Then we have the second layer norm, followed by the first linear layer with a GELU activation function, which matches what is defined in the attention is all you need paper. Then we got another linear layer, followed by dropout. When we return, we also throw in one final additional skip connection that's coming from the middle of the block. That's that second skip connection from our diagram. And that's the model architecture in a nutshell. I know that this is just a ton of information, and we don't have time to go into every single piece in detail. But the resources linked in the description below about how the transformer comes together are truly very helpful in getting that deep understanding of how it all fits together. So if you have some time to just sit down and work through it slowly, you'll be able to write transformers in your sleep. Once we have the model architecture defined, we still need to set up our training loop. This involves defining a loss function and choosing some optimizers that will operate on our model as it iterates over the dataset. Our loss function computes softmax cross-entropy loss and returns both the loss and the logits. We also define a single training step here, which computes the gradient of the loss using a helper function in NNX called value and grad. Unsurprisingly, it returns both the value of the loss function as well as its gradient. We then update the metrics that we're tracking, and finally, we'll use the optimizer to update the weights of our model based on those computed gradients. Now we are ready to train the model. We set up our specific optimizer, in this case the AtomW optimizer from the Optax library, largely because that's what was used in the original paper. We'll go ahead and start our tokenizer, set up our metrics, and create our training loop, which centers around calling that train step function that we just wrote. Then every 200 steps, we evaluate the performance of the model so far by computing the loss function against the validation dataset. Okay, so if you haven't already, go ahead and run that training loop to get things started. Next, I'll talk a little bit about accelerators and some considerations around them while the training is getting underway. Let's talk a bit about your infrastructure options when it comes to training with JAX. CPU, GPU, TPU, it all works. In a Kaggle notebook, you can have 8 TPU v3 chips to use for free for up to 9 hours at a time. This is quite a lot of compute and will allow us to train our GPT-2 model in 7 hours or so. Colab gives you up to 8 TPU v2 chips for free, with the ability to get more recent TPUs and GPUs with a Pro subscription. The v2 chips aren't as large or powerful as the v3 chips, and as a result, the amount of data we pass in per batch of training is smaller. Now, if you need even more scale, GCP allows you to pay for quite a lot more resources, allowing you to train very large models. On the GPU side of things, Kaggle offers both a P100 and 2 T4 chips, while Colab gives you an NVIDIA T4 GPU for free, and the Pro subscription, of course, grants access to much more, like the A100. GCP has an even wider selection of GPU resources to choose from, so you can customize to your heart's content. Just make sure you do turn them off when you're finished using them. Modern-day data processing and model training needs require distributed parallel processing to be efficient and effective. JAX is built for scaling up in this way, and it's easy to set up our model and data to operate across multiple chips through JAX's sharding rules. JAX knows about our multiple chips or devices, and we can create that mesh of these devices, which define our parallel strategies in code. And when we create our model layers, we can specify how each set of parameters should be distributed across this mesh. Let's check in on our training progress. Hey, it's looking good. We see that the TPUs are being utilized quite fully. The training and validation loss are coming down steadily, and things are generally moving along nicely. We'll check back in a while. In our Colab, we can see the outputs being printed, showing that we're getting through 200 training steps every 40 seconds or so. Since we're doing 50,000 training steps, we can expect this training run to take, 50,000 steps divided by the 200 steps per print statement, multiplied by the 40 seconds times, divided by 60 seconds, carry the 1, cancel the 0. It's about 166 minutes, or a little under 3 hours. It's not bad for some free compute. On Kaggle, since it's using a 3 times larger batch size, it'll take a little bit longer, but it is a larger trip, so it won't be 3 times as long. I've seen this take just under 6 hours or 7 hours to finish. Once training finishes, we'll be able to plot the loss on Colab directly. though you'll likely already be watching its progress on your weights and biases dashboard. The final parts of the notebook focus around the topic of model saving and loading, so that once you've trained your model, you can reuse it again and again and fine-tune it with additional data if you wanted to. Let's take a look at that code now. Orbax is a library made for saving and loading JAX model checkpoints. This code does some initial checks to ensure that the relevant file paths exist, and then it creates a checkpointer, grabs the model state, and then calls checkpointer.save with the desired path and that trained state. That's all there is to saving your model. Restoring a model is similar. If you don't have your previous model checkpoint handy, you can use one we've stored in Kaggle for this very purpose. This time, once we create our checkpointer object, we'll call checkpointer.restore, passing in the checkpoint path and the model state of an untrained model. The purpose of this is to encode the model architecture first, and we do this by calling our createModel function. Then we can put the restored state into the model by calling nnx.update, thus updating the model with the state. So it's been a few hours and the model has finished training. We can see that on both the Colab and on weights and biases, some of our results. The training and validation scores are there, as well as some sample outputs. You can also see that we've used our TPU resources quite fully. Pretty good for running a model directly in Colab. I've also tried training this model on GCP with 8 TPU V6s, also called Trillium. I was able to complete that training run in just 75 minutes. To do this, I bumped up that batch size to 144 so that I was able to get good TPU utilization. Now that's some fast model training. Wow, that was quite a long video. Thank you so much for making it all the way to the end. Hopefully you got your model training, even if it's not quite finished yet, since that might still take a few hours. So that's bye for now from me. Enjoy the rest of Google I/O, and I'll catch you in the next one.